Yes, sir. Rohit, thank you. Shruti, thank you. Good evening, everyone. Should we proceed further? My voice and screen is clear, right? Yes, sir. Thank you. So today we are understanding the IoT platform with ThinkSpeak. So in the previous session, we were working with NodeMCU ESP8266 and Blinky app. Now we are going to work ESP8266 NodeMCU with ThinkSpeak. So the step one is to set up the hardware and software. So what are the requirements we need? We need NodeMCU ESP8266, USB micro cable, and computer with Arduino IDE installed, and ThinkSpeak account. ThinkSpeak account is like this. Okay. So you need to have an ThinkSpeak account like this. If you are registered and if you are enrolled in the MATLAB ThinkSpeak account, you will get this kind of web page. For this web page, you are able to see the web page. My Google Chrome. Is everyone able to see my screen completely? What I am showing is ThinkSpeak web page in Google Chrome. Someone please confirm. Is it clear? No, sir. Now we are able to say yes. Okay, okay, fine. So as per our PPT, the last concept is we have to connect ESP8266 NodeMCU with ThinkSpeak. In the previous session, we were having the connection with Blinky app as an IoT application. That is Android, iOS, or web application. The same way we have ThinkSpeak analytical app. So this is having MATLAB inbuilt tool. So we are going to connect ESP Node MCU 8266 development board with micro USB for programming with the computer Arduino IDE installed with ThinkSpeak account. So we need to register with ThinkSpeak. So we'll get this account. Next is we need to install Arduino IDE. After installing Arduino IDE, you need to paste these URLs, okay, in the Arduino IDE to get connected with ESP8266 compatibility boards. Clear? This is how you need to do. Preferences. I will be showing you from my side how I have done this. So this is my Arduino IDE. So this URL you have to copy and you have to go to tools or file preferences and you need to paste it here. Is everyone clear so far? So this is we are getting connected to ESP8266 Node MCU board with this URL. So this URL will add the board manager drivers to our Arduino IDE. Then only we can connect this ESP8266 module to Arduino IDE. Okay. Next. Next is board. In the board, you need to select tools, board, board manager. You need to type here. Okay. So this board manager, you need to type here ThinkSpeak. So ThinkSpeak is not available directly. So it might be included with the ESP8266 library itself as the software. Okay. So this is advanced Arduino IDE. So this is the old Arduino IDE. So this is 1.4 version. So might be it has included directly in the code. If that is not included, we will get an error in the code. Then we can add the library manually. Next is we need to select the board with the following settings using CPU frequency, COM port connected to COM4. Okay. And the upload speed is, what is the upload speed here? It is selected 11.5200. That is the baud rate. Correct. Next is flash size and the board name. ESP8266, ESP12 module. Clear? Next is coming to the ThinkSpeak. In the ThinkSpeak, you have to create a new channel. In the new channel, the channel name you have to provide. Okay, that is signal strength. Signal strength. Signal strength. Next is RSSI. That is nothing but received signal strength indicator. Field 1. So I'll minimize and put it aside, side by side. Click save channel. Once you save the channel, you will get some channel ID and its connecting buttons and API keys also. That is the most important. In Blinky also, we have got that key. Write the Arduino IDE code to connect to Wi-Fi. So we have already the Wi-Fi. Open. There was some code. Arduino IDE connect to Wi-Fi. When was that? Documents. Next is measure the Wi-Fi signal strength RSS. Send the RSSI value to ThinkSpeak. Select the correct board and port in the Arduino IDE. Click and upload the button code. Monitor the data in ThinkSpeaks. Okay. How we have to write the ThinkSpeak board, that we need to understand. This example shows how to collect the environmental data from the device and post it on your device to ThinkSpeak channel. This example uses ESP8266 and ThinkSpeak communication library. So whatever we are including in the ESP8266 NodeMCU Arduino IDE, we are including Wi-Fi module, ThinkSpeak library, and what else we are including? The ThinkSpeak channel library. Okay. The supported hardware for ThinkSpeak are ESP8266 12 and 12E. So we have ESP8266 12. So ESP8266 has inbuilt ADC. So there is some ADC pin which is on the port A0. Okay, the top port here. This is ADC 0. So there is only one ADC on the ESP8266. So the most important example here is we are posting the temperature data and read from channel. Okay, so based on this, we are going to read the ADC value. This is a temperature sensor LM35, the black color one. And here are some resistors. So the VCC ground are connected directly to the temperature sensor, and data pin is connected directly to the middle pin. The data pin is connected to the A0 pin of ESP8266. Next, setup. So similarly, we are going to create the channel name and the channel ID. Okay, so we are going to see what is the office temperature. Field 1 is temperature in Fahrenheit. Field 2 is temperature in Celsius. And field 3 is elapsed time. And field 6, field 7, field 8. These values, we are sending it to some storage value. Like we are going to read it in storage. Storage is nothing but either you can send it to cloud or either you can send it to AWS, Azure, GCP or anything. Next is using this field 6, field 7, field 8. Okay, we are going to calculate or calibrate the simplest form of data. Give me a minute. Sorry, there was an interrupt. Okay, so Field 1, field 2, field 3 are the data which we receive from sensor, and we are going to calibrate or store this data field 6, field 7, field 8 into cloud. Next is, if you want to go for a practical approach, okay, whatever the required hardware that is mentioned here. So LM35 sensor can be directly connected to the ESP8266. Just for safety, for the current limiting, we are using the resistors. Okay, as we have the basic principle for limiting the current, not to spoil the device. Okay, this is how we are going to bias or connect ADC A0 pin of ESP8266 with LM35 sensor. Okay, whenever we power up the LM35 with ESP node MCU, okay, so this will capture the data from the environment in the form of voltage. That voltage will be send it to node MCU, and node MCU will read the analog data in the form of voltage, and we are going to calibrate, or we need to use some formulas to convert it into temperature reading, either in Fahrenheit or Celsius degrees. Clear so far? Everyone understood? Please someone respond. So my team will provide you this presentation, code, and everything. You people, if you are interested to do the practical part, you can get the board in the Amazon or in the market. Okay, you can order online. The same way what I am explaining in the slides, you follow those connections and you'll get the results. If you face any difficulties, you can just drop a mail or use our group account to ask the questions. My team will respond you to help you. Okay, is this clear, everyone? Should we proceed further? Yes. So the next topic that we are going to cover is this is the most important topic for an embedded application engineer. Okay, so embedded hardware engineer, embedded firmware engineer, embedded application engineer. So embedded application engineer, those who are working on the application level, the people who have written the drivers and they have to build the application. Okay, the engineer who has to build the application on the boards and interface the components. Suppose, consider an example. Okay, you are having a high-end top model car. Okay, which is filled with 7-seaters. That 7-seaters car is covered with 6 airbags. Okay, front, back, and 2 sides. So how you are going to interface these 6 airbags, and what action or what reaction it has to take care. So we are going to use I'll use paint also to explain. So this is your car which has 2 airbags in the front and 4 airbags in the side. Okay, so has back is completely storage. It doesn't require any airbags. So these all are airbags. So what should be the integration part if my car gets crash? This is my MC microcontroller. Okay, so all these airbags are connected to a microcontroller unit. Okay, they are not connected directly to the microcontroller unit. Their on off, their mechanism on off is connected to microcontroller unit. These airbags should be filled with air. They are connected to a container. Air container. That is nothing but air cylinder. We have some air cylinder in the cars where when we get a crash, this air cylinder will eject the gas or air into the airbags and it will open up to save the lives of humans in the car. So how this action is going to happen? Using a microcontroller unit. So if we write a firmware, okay, the firmware code might be having bugs. And practically, it has to monitor each and every movement of your car, and it has to calculate the speed, it has to calculate your wheels, it has to calculate your steering, it has to understand the behavior of driving. Okay, so taking all these into consideration, your microcontroller becomes alert. If the microcontroller becomes alert, if there is a situation coming for crash, okay, how it has to react. So for these kind of systems to build, okay, we are going to use real-time operating system. And most of the times, if you see the dashboard of aeroplanes or aircrafts or missiles anywhere, okay, or some satellites, these are all machineries or equipments or nuclear reactors, even thermal power stations. These all will run on real-time operating system. So we are speaking more about real-time operating system. What is this? We'll go into the slides and understand. Clear so far? The example. How it is going to work, I am going to explain it. So introduction. A real-time operating system is a special type of OS specially designed for embedded systems. So RTOS is only for embedded systems. Windows, Linux, okay, Android, iOS, these are general purpose operating systems. A specially designed operating systems to work on only on embedded boards. Then it is called as real-time operating system. Is everyone following? Understanding? Yes or no? The people who are good at OS programming are the students who knows more coding, okay, writing in Java, writing in C++, writing in embedded C, and scheduling. And those students should have a career in real-time operating system. Okay, this is how the basic skill set required for a real-time operating system engineer. Real-time operating system engineer should have firmware knowledge and microcontroller boards knowledge and OS programming knowledge. Okay. The basic structure of real-time operating system is from the bottom level, we have microcontroller board. On that board, we are going to build firmware. And for that firmware, we are going to write real-time operating system kernels. Kernel is nothing but the heart of operating system. Okay. So on top of RTOS kernel, we are going to develop application. Application is nothing but software programming. Clear someone? Everyone? Custom hardware, board drivers, real-time operating kernel system, and application. This is simple structure of our real-time operating system. If we go to general purpose operating system, we have a hardware, we have firmware, we have drivers. Okay, on the top of drivers, we are going to use directly the operating system. But there is no application. Whatever the application we want to install, we are going to install in our laptops like Windows, Linux. If we want to install Firefox, okay, Firefox can be installed. If you want to install Microsoft Windows, Microsoft Office, we are going to use MS Office. But here the application means to control the airbags, to control speed alert, to control dashboard of an aircraft, to control missile prompting. These are the applications on a real-time operating system. Clear, everyone? Proceed further. Yes, sir. Raja, thank you. Yes, here we have come up with a slide. General purpose operating system versus real-time operating system. The basic difference of using general purpose operating systems on real-time operating system lies in the nature of a system, that whether the system is time critical or not. Time critical. Time critical is nothing but, see, consider an example. The aircraft. When we press the button before landing on a 200 meters of altitude, the wheels has to open. This is time critical. If you are installing Firefox, but the Firefox is getting crashed, okay, in your Windows operating system, is that time critical or not? Definitely it is not. We can install another time. But if we are going for the aircraft, if we are clicking the button on a 200 meters of altitude, okay, to open the wheels, it has to open. Else, the plane is going to crash. That is the main difference between general purpose operating system and real-time operating system. When we hit the car with an accident, the airbags has to open. If the airs are failed to open, it's a failure and it is not time critical. The RTOS is not working properly. Right? So only many of the car manufacturing companies or the aircraft critical team, they are going to test the aircrafts before they are going to launch in the field. So only they will give us test drive. Hope everyone is clear. General purpose operating system versus real-time operating system. Yes. Thank you. What is real time? The ability of an operating system to provide a required level of service in a bounded response. As I've explained you, altitude of 200 meters, my aircraft has to open the wheels when I click the button. Right? That is, we have a time critical of response time of 200 meters of altitude. If we suddenly take off from the 200 meters of altitude, what will be the air traffic condition? And it is against the protocol. And it is failure of the aircraft. Then what landing technique has to be used? They will have some alternate, but it is timing critical. So only it's the failure of our real-time operating systems. The definition comes here. The ability of an operating system to provide a required level of service in a bounded response time. We have a particular time span. It has to respond. It has to do the task. Else, it is a failure of time critical. Here on the slide, we have an example of airbags. Clear? Proceed further. Dear students, you are with me? You are sleeping. Shake. Thank you. Sriranga Sai. Nani. Vasavi. Thank you. Thank you. Yes, yes. Everyone is following. Understanding. Right? So this is all theoretical. When you go for the OS programming and when you are going for the application level, then you will be having the programming concept. And you will be having many flavors of operating systems in RTOS, like free RTOS, VxWorks, real-time operating system, RTOS, and all these are different flavors of operating systems. Based on the board, based on the memory, you need to choose your real-time operating system. Okay, so that is a different career in embedded systems. What is RTOS? It is a response to inputs immediately. Here the task is completed within a specified time delay. In real life, situations like controlling traffic signals or a nuclear reactor or aircraft, the operating system has to respond quickly. See, again, this is an past example of Hiroshima, Nagasaki, Japan. Okay, the nuclear reactor, there was a failure of real-time operating system. It has become an atom bomb. The nuclear reactor failed functioning and it has blasted, and still there is a desert area in Hiroshima, Nagasaki. So this much disaster happens if the real-time operating systems fails. Next, types of real-time operating system. There are soft real-time operating systems and hard real-time operating systems. If you have any questions, please let me know. I'll proceed further. Thank you, Nani. Sheikh, thank you. So there are two types of real-time operating systems, that is hard RTOS and soft RTOS. A hard real-time system has timing critical deadlines that must meet, otherwise a catastrophic system failure can occur. Example, air traffic control, vehicle subsystem control, nuclear power plant. See, air traffic control. If we see the air traffic control, okay, the air traffic control is nothing but the staff, those who are giving radar signals to the flight pilots, whether to take off, land, or just to fly for another 2 seconds or another 2 minutes. This is completely based on air traffic control. And the runway is not clear. Okay. On the runway, the flight is landing and the another flight is taking off. What will happen? There is a mismatch in the air traffic control. Then the two planes gets crashed. Right? If the speed is very high, they may take off and they may land easily. If that doesn't match with the speed, then there is a collision. This will happen in hard RTOS. Hard RTOS are very timing critical. They are hardware based. Next is soft RTOS. In a soft real-time systems, deadlines can be occasionally missed. Okay. That is example, multimedia player controls, cellular networks, websites and services, computer games. See, we have a dashboard in our car, okay, which is having multimedia music player. When I click on the media player, my FM is turning on. And when I click on USB connect, Bluetooth getting connected on. If this happens, there is no timing critical. So I am using 5G network and I am getting only 2G network. My call drops are very high. Then I am trying to redial. Is there any criticality in this? No. And I am trying to log into a website and the website services are too slow and the page is loading very slow. Example, our results website. Okay. When I was studying in my SSC and intermediate, okay, the website used to open very slowly. It means it used to take almost 5 to 10 minutes when I enter my hall ticket. And I have to sit in the computer center and wait for 5 minutes or 10 minutes. Even some people are in the line also. And all of a sudden, what the computer operator does is he will open n number of web pages or web tabs. And he'll enter all the hall ticket numbers. And here the traffic on the website is very high. Does it create any mistake for us? We have to wait. Nothing happens. We'll get the result. Already the results are out. They are displayed on the websites. Okay. After 1 hour, after 2 hours, after 3 hours, after 5 hours. Some or the other way, we are going to observe our results. Next is computer games. So most of the PlayStations. Okay. In the olden days, we used to have Mario. Okay. The fighting games. Okay. These kind of games are built on freeware RTOS. And the commercial computer games, they are built on the PlayStations like Sony. Okay. They are built with VxWorks and different kinds of real-time operating systems where they can play football, volleyball, or shooting games, or any kind of graphical games. If this game is stuck, will it create any critical help for us? No. Nothing is going to lose. We may lose some small amount of time. But whereas hard RTOS, we are going to lose the lives. We are going to see the disaster. So this is the importance of hard RTOS and soft RTOS. Clear everyone? On the example basis. Hope everyone is with me. Understanding? Yes, Raja, thank you. Murli, thank you. 417, who is this? What is the name of rule number 417? Ramya, thank you. Sharif, thank you. Harshavardhan. Bejanki. You are from Karimnagar, Bejanki. Next. I'm moving on to the next slide. Functions of RTOS. Whatever it is hard RTOS or soft RTOS. Okay. What are the basic functions? Task management, scheduling, resource allocation, interrupt handling. These are the more important 4 concepts of RTOS. Task management, scheduling, resource allocation, interrupt handling. What is task management? In real-time applications, any process which takes a specified execution time and occupies predefined amount of memory is called a task. So my task is to eject my aircraft wheels at a 200 meters of altitude. Okay. The execution time takes is 2 minutes. Okay. To come from 200 meters altitude to 50 meters altitude, it takes 5 minutes. Or even the flight time, it can increase based on the release of the wheels. Okay. When it crosses 200 meters altitude, it has to land definitely, as per the protocol of aviation. But from 200 meters to 50 meters of altitude, it takes around 5 to 10 minutes. So to open my wheels, it takes 2 minutes. So it is consuming time, it is consuming memory, it is consuming my CPU. Task management is a process of managing tasks through its life cycle. What is the life cycle? Pilot has to initiate a call to the passengers that we are going to land in another 7 to 10 minutes. In another 7 to 10 minutes, everyone tightens their seat belt. And in that 7 to 10 minutes, he will press the button to release the wheels. And on the 5th minute, the wheels got released. And in another 5 minutes, he is going to land on the runway. And by the time he is going to park the plane, it will take almost 10 to 15 minutes. This is how the life cycle comes for a aircraft. Similarly, we are going to define the life cycle for the car, missile, or any kind of equipment. Task states life cycle. Okay, create a task. What is a create a task? The task is to create eject of wheels. If I am ready to land, if I am ready to take off, my wheels has to close, or else if I am landing, my wheels has to open. If the task is ready and it is functioning correctly, then it has to go to running state. Okay. From the running state, it can go to suspend or it can go to block. If it is blocked or suspended, it is critical. Then we have to wait it to check for the ready again. That's why the cycle is rotating ready to running and running to suspend, suspend to block or running to block. If ready to running is smooth, then it is successful. If the running is failed, then it has to go to block state or it has to go to suspended state. Or we have to delete that task. Clear so far? How the task life cycle is going to be? Simple. This is a flow chart. But we may have some intermediate states when we are going to create and declare a task. Okay. Clear so far, everyone? Right, Narsimha, thank you. Task process states. Each task process can belong to one and only one state. That is, as we know, in algorithm, we will create a start. We will have state 1. We will have state 2. We will have end task. Okay. The similar way, each and every start has its own identity and they are belonging to only one task. They are not belonging to multiple tasks to schedule. If start state is there, the task has to start. If state 1 is there, what it has to do? It has to do that task. If state 2 is there, it has to enter into the state 2 task. If this is failing, then the system is getting failed. Transition to and from the ready queue are based on the availability of resources or time resources available. This is my embedded board. Okay, I have microcontroller unit. This is some RAM. This is some process and some interface functionality. If all these three are correct, then each and every state gets executed correctly. Typical task operations are creating a task, deleting a task, controlling task, and scheduling task, obtaining task information. So from each and every task, we are going to obtain some information. What is that information? Whether the state is going to run, or it is going to suspend, or it is going to block. This kind of information we are going to get it from each and every task. Clear, everyone? If you have any questions, please post it. Should we proceed further? Sriranga Sai, right? Thank you. Harshini, thank you. Yashwant. Small project using Arduino, but big project, what should be used? So if you want to go for a big project, we can use, this is out of syllabus question, Murli. Okay. ARM board. Okay. Or Raspberry Pi. Or you have many other boards also. Okay. Whatever it might be, your application should be defined in such a way that it should have real-time usage. Okay. So you can use BeagleBoard, Black. These all are boards which I have worked long back. BeagleBoard. Next is Intel Galileo. Next is ST Micro. These boards are very famous. ST Micro. They are used very much in real-time operating systems in cars. Okay, by Bosch company. Okay, so these are the boards for the real time, and they can be developed on the product level. And there are few smaller boards also. I don't remember the number and name of the boards. When I get into that, I'll let you know. Okay, using those boards, we used to work on smart gadgets like pagers, smartwatches. Okay, those kind of boards. These are standard boards for embedded RTOS or high-end applications where they use in aircrafts, our cars, missiles, and everything. Okay. Clear so far, everyone? Murli, did I answer your question? Yes. Thank you, Murli. So proceeding further. Scheduling RTOS, the main function. So what are the, we have discussed in some slide. Functions of RTOS. What are the functions? Task, scheduling, resource allocation, interrupt. So The task part is clear for everyone, right? Basha, thank you. You are the person who are attending my class. Harshini, yes. Raja, yes. Pandana, yes. Right. So task management is clear. So how we are going to create a task, how we are going to assign the states of the task, and now we are going to understand scheduling the task. Task management provides the following information about tasks: number of tasks, resources requirement, release time, execution time, and deadlines. Okay. So aircraft is not only just controlling the wheels, but it has to control the speed of the flight, altitude level, and the oxygen level in the aircraft, and it also manages speed also. If you are taking an example of our automobile car, okay, my car has to monitor speed, fuel consumption, air condition, engine heating, battery status, air filter status, oil cooling status, engine coolant status, bulb status, and all these things. Those all are number of tasks. To manage this all tasks, what are the resources required for my microcontroller board? And there is a huge rain suddenly. Okay. And the road is single road. There is a truck ahead in 500 meters. The release time should be very less to turn on my glass wipers. Is the example clear, everyone? Followed? Understood? Yes, yes. So the number of tasks for monitoring my car are tire air pressure, AC, cooling, engine heating, fuel consumption, speed, okay, lights, wiper, and everything. These all are the parameters which are going to measure. Those all are tasks. To run all these tasks, I need some resources. So the resources, are they sufficient? Are the requirements are meeting? Yes, my microcontroller board supports all these requirements to run the tasks, all on parallel. Okay. Coming to the release time. The release time is nothing but there is a huge rain. Example. My wipers are to on automatically. Okay. I am traveling on the road. My headlamps has to turn on. Okay. If my screen is blur, my windshield, okay, it has to spray some gas to make it clear. The fog should be controlled automatically using auto option in my AC. Okay. Next is execution time. Execution time should be based on the scheduling. Okay. My car petrol is 5 liters, but my car mileage is 15 kilometers per liter. If it is 5 liters, then I can travel only some 60 to 70 kilometers based on the load and AC consumption. What it has to do? It has to give me an alarm. or it has to slowly go into an efficient mode or eco mode to consume less power or less fuel. That is execution. Next is deadlines. Deadlines are nothing but the task is running. If it is still running, okay, either it has to go to suspended state or blocked state, or it has to complete running. Then it is called deadline. We are driving my car in a hot summer. Okay, my car is running very smoothly, and after running some 80 kilometers, the coolant is getting heated and the radiator fan is getting turned on. This is a task, and this has a deadline to turn on my cooling fan. Hope clear? Understood everyone? The coolant can make the engine cool as much as it is running fluid in my engine. But to make the coolant to cool, I have to give the air to my coolant. That is how my radiator fan has to turn on. That is the deadline. When it is reaching the threshold value, my radiator has to turn on to cool the coolant. There are some scheduling algorithms. Okay. So what are those scheduling algorithms? Let us look into it. Scheduling algorithms in RTOS are clock-driven scheduling, round-robin scheduling, priority scheduling. Okay. Clock-driven scheduling, release time, execution time, deadline will be known well in advance. Okay. So my wipers has to release. Okay. So when the car crashes, immediately it has to note down the value of the crash and it has to release the airbags or the engine ignition should turn off. That is the execution time. Next is radiator cooling. That is the deadline. So this is how the clock driven scheduling happens practically. This all we have done in Bosch using ST microelectronics boards. Okay, for the Bosch company. We used to design these kind of scheduling boards and everything to some luxury cars. So we don't know the customer, but we used to program these kind of things. Schedule can be computed at some regular time, instances, minimal runtime, overhead. That means there are some less scheduling tasks. If they are taking some more time also, it is okay. That is, I have 5 liters of petrol. I can run up to 70 kilometers. Still the alarm is giving. Okay. After driving 50 kilometers, it has to go into eco mode. And still you are running, but you are not finding a petrol pump or a fuel filling station. That means you are running scheduling overhead time. But it is very important to refuel your car. So these kind of systems, clock driven scheduling is not suitable. Whenever the trigger happens, then only it will give us the output in scheduling of clock driven. Sanjay, we'll talk later about it. Okay. Next kind of scheduling algorithm is round robin scheduling. Round robin is nothing but jobs are scheduled in the form of FIFO. FIFO is nothing but first in, first out. whatever the task comes first in the queue. Queue is nothing but a line. So we have a line in a bus stand to board the bus. Okay. So everyone has to go in a queue. The person who is standing first in the queue will go into the bus first and take the seat. So the same way round robin scheduling happens, first in, first out. Here we don't have the prioritization. So if it is an important task, if it is round robin scheduling, then we have to wait until that task has to come. If job A is running, okay, we cannot make the job B as important and run the job B to halt job A. That is not possible in round robin. Unless until job A is running, we cannot proceed further to execute or start the job of job B. So most of the times we will not prefer round robin scheduling also. Next is priority scheduling. This is the most important one. The processor, the RAM, and the board utilization is completely 100% in priority scheduling. Processor has a capability of runtime scheduling or already scheduled jobs running. We can give the priority. Suppose example, we have hardware reset. That is a highly important. That is a priority for that scheduling. So directly when I press the power button of my laptop, it will be asking you to shut down. Still there are some jobs running. If you cancel it, it will cancel. That is how the priorities are assigned. This is a general example we are going to see. But whereas in real-time operating systems, these all are scheduled based on the coding part in the OS. Okay. Is everyone clear with this so far? Scheduling using clock-driven, round-robin, and priority. Most of the time, in real time, we are going to use priority-based scheduling. Even though they are round-robin, even though they are clock-driven, based on the coding, we are going to make them as priority at runtime or at design time. Is this clear so far? Everyone understood? Followed? Raja, yes sir. Sri Lakshmi, yes sir. Spandana, yes sir. So only 3 people are listening. Shaikh, Susmita, Balaji, Namita Reddy, Sirisha, Dasar, Mahesh Chari, Aishwarya, Nasiruddin, Koti, Anjali, Bhavita, Priya. Yes, Hemant. Thank you. Praditeja. Sriram, Chandrasekhar Naidu, Harshavardhan. Thank you. So everyone seems to be slightly attentive. So everyone is posting yes. So some are posting yes. Okay. Continue. The next concept is resource allocation. We know that embedded system have limited amount of resources like CPU, RAM, and power. So whatever the tasks or the jobs that we have scheduled has to be assigned efficiently to my memory and CPU. Based on the application or based on the usage, we can schedule the algorithms again and again for the resource allocation. Okay, this is how the resource allocation happens on the board level or the hardware level for tasks and schedules. Next is interrupt handling. As we know, the interrupt definition, it can be a software interrupt or a hardware interrupt. I am executing some program and there is some intermediate program, then it is called a software interrupt. Okay. When I am executing program, I am doing some keyboard entries, then it is called a hardware interrupt. Okay. Everyone is able to listen, understand my voice? Yes, sir. Thank you. Please, please. Thank you. Interrupt causes the processor to suspend if the jobs are running and some code is running or if the program is running, whether it is a software interrupt or a hardware interrupt. That hardware interrupt or software interrupt is given more priority than the normal code of execution. This is how the interrupts are handled. Clear so far? Functions of RTOS. Task management, scheduling, resource allocation, interrupt. Clear, sir. Charishma. Parhas. Sriranga Sai. Yes, sir. Clear. Right. Next, coming to popular real-time operating systems. Asif, thank you. Sheikh Saiga Banu. Thank you. Popular real-time operating systems are VxWorks, Linux OS, RT Linux, Windows CA. Okay, these are some popular real-time operating systems used in the industry. VxWorks is the topmost one. Okay, so these are licensed operating systems. Apart from this, we have pre-RTOS, real-time RTOS. Okay, these are some freeware where we can download it from the internet and boot load into the microcontroller board and write some scheduling and jobs. So applications of RTOS. Real-time operating systems are used in military engineering applications and data communication systems. Military is nothing but missiles, armed weapons, and all those things. Next is engineering applications. Engineering applications like CNC machines, okay, CAD drawing machines, civil engineering machineries, and data communication systems like cellular towers or cellular base stations or satellite base stations. These kind of applications use real-time operating systems. Okay. Apart from this, automated missiles and space satellites are also powered by RTOS these days. So to save energy, okay, so there is a satellite example. Okay. If we are launching the satellite, it has to consume huge amount of energy and it should be turned on for some amount of days and hours. Okay. Once we see that satellite is launched, then we can turn on all the subsystems. That using RTOS we can program. How we will be knowing that the satellite is landed properly? That is also by geotraffic location. Using the geo-targeting and the arbitrary location by calculating the latitude and longitude and altitudes, okay, we'll get the landing point of satellite. Then to save the energy, we will be using RTOS to power up all the subsystems. If there is any embedded system application, okay, suppose example, consider your washing machine. Okay, so Your washing machine need to run on real-time operating systems. So intermediately, you can make your washing machine to program, to make the water heat, to take the detergent automatically, to fetch the water from the tap immediately. And all these can be programmed using real-time operating systems, using washing machines like IFB, Bosch, or IR. These are coming with a real-time operating system boards. Clear so far? Advantages of real-time operating systems. Sushmita, yes, thank you. If you have any questions, please post. I'll wait for 1 minute. Attendance link will be sent. Okay. No doubt, sir. But ASC Prasad, is there any alternative if failure happens? So, as we have seen, hard RTOS and soft RTOS. So, hard RTOS, if failure happens, it is a disaster. Okay. If it is a soft RTOS, okay, if failure happens, we can arrange some alternate way. So, if we do some hardware reset or if we do the reboot, then it will come to proper functioning. PS Prasad, did I answer your question? Prasad. So, as I have said you example, the critical part, airbags of your car, that is hard RTOS, or the aircraft releasing the wheels, that is hard RTOS. If it is soft RTOS, like your washing machine control, okay, you have scheduled for 33 minutes or 40 minutes with hot water with 10 milligrams of 10 grams of detergent and 4 liters of water. This is how you scheduled your clothes washing using washing machine. If this fails, what will happen? You need to turn off your washing machine and turn it on back after 5-10 minutes. Okay, this is how we are going to use RTOS. Sunil Joshi, we have covered 2 topics today. One is real-time operating system, and the other one is IoT based ESP node MCU interface with ThinkSpeak, that is MATLAB. Clear? Yes. Any more questions? Please post. So, Pawan, hopefully ESP8266 node MCU. I'm not sure. I have never tried that to download and install about real-time operating systems. But on ARM boards like LPC2138, LPC2148, these are some NXP boards and ST micro boards. So on these boards, I have worked with real-time operating systems, VxWorks. Okay, just for job scheduling. Okay. So already the tasks has been created. So for that tasks, we have to do some tests. So the tests we have done using job scheduling. Once and tell me about today topic names are. So today topic names are embedded systems, real-time operating system, and how we are going to use that real-time operating systems in practical. And the second one is Node MCU ESP8266 interface with IoT ThinkSpeak MATLAB application. Okay. Coming to the slide presentation, advantages of real-time operating system. So the attendance link is not working, I think. Please resend it, the proper attendance link. So the advantages of real-time operating system. RTOS can run on applications in any diverse and challenging environment conditions. So the hard RTOS are every time challenging environments. Soft RTOS, they are moderate or less challenging environments. RTOS will run more efficiently or more promptly on limited number of resources like 2 GB RAM and 400 MB of SOC, ROM. These kind of boards we have used. So 400 MB is very less. Okay, not at least 4 GB. So we used to interface 8 GB, 16 GB SD cards. Okay, to run the OS application. It consumes less power and memory. Okay, less power anyhow it is there. That is 5 volts or 9 volts, hardly 12 volts. So we have a car battery of 12 volts. Okay, more than that it cannot use. That is also DC power. Okay, it will mostly run on 5 volts and 9 volts. And the memory is 2 GB RAM, hardly 4 GB RAM. The maximum size. Kernel size is also very small. That is, the kernel size can be almost all 10 MB or 12 MB. Okay, so the Linux kernel, whatever the program we have dumped with VX works on the ST micro boards or LPC2138 boards, the ROM size was around 400 MB. Okay, and the kernel size was around 12 to 15 MB. That's all. Okay, these are the prioritized advantages of RTOS. So if you have any questions related to RTOS, ESP8266 node MCU, IoT, ThinkSpeak, whatever it is, okay, please let me know. How should we proceed? And I'm giving you an option. If someone wants to cover some specific topics, please tell us. Ramya, not washing machine motors. We are interfacing that motors to our microcontroller board embedded systems. But some premium washing machines, we are assembling it to a real-time operating system OS. Okay, Ramya, did I answer your question? Okay, sir. Thank you. Nandini, the attendance link is not working. Or the Blackbucks team, please check the attendance link and forward it to the students or our participants. Okay, attendance is very important for them. Thanks. Link will be activated at 8:45. Real-time operating systems, IoT, Node MCU of MATLAB. These are the topics that we have covered. So the MATLAB, we are using a product called ThinkSpeak. Sir, can you again differ the real time and critical time? So the real time and critical time are like this. So based on the RTOS category, we have two types of RTOS, that is hard RTOS and soft RTOS. So if the hard RTOS is there, that is timing critical. If it is soft RTOS, it is less timing critical. In the real time, if we see an example of car met with an accident, then it is a hard RTOS, timing critical. To save the lives, we have to eject airbags. That is hard RTOS and timing critical and real time. And the real time OS which is running on our media player in a car. Okay. Then I am clicking the button of media player. My FM is turning on. Then what I am going to do? I am going to reboot my media system. Then it is going to give me the proper functionality. This is soft RTOS. This is not that timing critical. It is prioritized, but it is not that timing critical for a disaster. Clear? Someone was asking me the question. Yes, sir. What is your name? 4 stars or 5 stars? It is 4 stars only. Easy. So you can download the VxWorks WinRiver. Okay. So by registering an account, if you are having a corporate account or if you are working, okay. So these all are the supported platforms. It will support Raspberry Pi 3, Raspberry Pi 4, NXP, okay, ARM boards and microchip boards and RISC architecture boards. Supported platforms. These all are ARM boards, ARM processor, LPC2138, LPC2148, 1768. These kind of boards, okay, they will support VxWorks operating systems. It is not freeware to download. Okay, you should have a corporate account to download and install it. It is paid. And there is some free RTOS also. This is completely open source. You can download the free RTOS, whichever is the latest version, and check for the platform or the board where you can run it. So most of the ARM platforms supports, or FPGA boards from Xilinx also supports free RTOS. But check for the compatibility. Okay. Is everyone clear so far? VxWorks is the commercial one and free RTOS is the open source. Okay, everyone is able to see my screen, right? Yes, yes. So getting started, if you click, so how to start and how to download the libraries, and you can directly, without having any boards, you can directly run your free RTOS on your AWS account also. If someone has AWS cloud account, and you can choose the emulator board on the AWS account and just check which board can run the pre-RTOS. And you can write your tasks, scheduling, resources, and if you have any interrupts, you can write that interrupts also. So all the PPT slides, codes, and registration links for RTOS or registration links for ThinkSpeak, everything will be sent in the form of a material in the final. Blackbucks team, will you answer Mahesh? Deadline for any tests or anything? Okay. So mostly there are no disadvantages. So there are limitations. So instead of saying those disadvantages, we will call as limitations. So most of the times, the commercial part of the real-time operating systems never fails. Why? Because they are fully tested. Okay. So if you are writing some tasks or scheduling some tasks, okay. So someone was asking the question. 417. What is this number name? Okay. So instead of calling them as Karishma, so instead of calling them as a disadvantage, okay, we call them as limitations. So the limitation is like this. Before launching any real-time product like aircraft or missile or any RTOS based application, okay, they are going to test in all possible cases. So when we go for a car launch, before the car launch, they are going to do some test drives. They are going to drift the car from above from 100 meters of height, 50 meters of height, how it going to release the airbags and how it is going to protect the lives of the human critically. Instead of calling disadvantages, we call them as limitations. Most of the times, most of the times the RTOS never fails. If that is fails, then it is very critical. That if that is hard RTOS. If it is soft RTOS, we can go proceed further by resetting or rebooting or power off and power on. Okay. So next upcoming classes, I will be teaching you the understanding of Python and the programming about Raspberry Pi and Raspberry Pi using IoT. These are the concepts we are going to cover in the future sessions. Basic microcontroller at Mega 328, Arduino, embedded C programming with Arduino, and some practical examples of Arduino like interfacing, LED, sensors, and UART. These are all completed with Arduino IDE. Next is ESP8266 node MCU with IoT application. Understanding about ESP8266 node MCU. Okay. Pin diagram. Interfacing ESP8266 with sensor with output LED and GPS with serial communication using UART or I2C. So all this has been covered using ESP8266. And coming to the IoT part of ESP8266, we have used open source Blinky app and ThinkSpeak app. Blinky app can be used both on the mobile phones or web application. And next thing is ThinkSpeak. ThinkSpeak is completely web application. It is analytical based web application. And next thing is the main important part of embedded system is real-time operating systems. So real-time operating system, this is all theory. So this doesn't have much practicals. If you want to go to practicals, we need to have operating system. We need to have programming of OS, and we need to have commercial operating system like VxWorks. And in the future, we are going to cover about Python, Raspberry Pi, and Raspberry Pi integration with sensors and sending that sensor data to IoT based applications. Clear so far, everyone? Yes, sir. Thank you. So here ends my session for the day. If you have any questions, I am happy to answer your questions. Good night, everyone. And I thank you, Blackbucks, for organizing this very scheduled manner. Thank you, everyone. Good night.